first speaker in the second part of the morning session is from Université Pierre et Marie Curie in France, Professor Jacques Fraissard. He will speak to us on Bronsted acidity scale of solids by NMR spectroscopy application to superacidic solids, and his co-authors are Drs. Badamac, Roy Grimmer, and Semmer. John.
Thank you. So I'm talking about a new technique that we have proposed a few years ago in order to determine an acidity scale of solid. I give you here the name of the different co-workers, and Sommer, who is working on sulfated zirconia. Erimu has just finished her PhD. Patrice Batamac, who is really bright. It was very good when he left my lab, but he spent 2 years with Georges Jola, and so he came back super good, of course. And some others. As you know, well, it is a new technique, so we have to give you some information about the technique itself before giving some results concerning superacidic and non-superacidic solid. As you know, the problem of determining the acidity scale of a solid, in my opinion, has not been yet resolved. Of course, there are many techniques for determining the acidity strength of the solid, but the number of these techniques proves that none of them is really valid. There are two ways for studying the acidity strength of a solid. Either you look at a bare solid using some spectroscopy techniques, or you study the interaction between the solid and an adsorbed phase. We proposed in 1976 at the International Congress on Catalysis to use the chemical shape of the proton for determining the acidity scale of the solid, because we said that the acidity must reflect the ionic character of the OH bond, and as the chemical shift gives the electronic environment of the proton, we should have a relationship between the chemical shift and the acidity strength of the solid. And this has been very well developed by the team of Professor Fraissard in Leipzig. And as we have been the first to say that it could be possible to have such a relationship, it's easy for me to say that this is completely wrong. And it is wrong for two main reasons. The first is true that when you have an isolated OH group, the chemical shift reflects the ionic character of the OH group. But you never know what is the exact environment of the OH group in the solid or at the solid surface. And the influence of hydrogen bond on the chemical shift is much more important than the influence of the ionic character itself. For example, we have found a few months ago some silanol group, not acidic at all, with a chemical shift of 7 ppm because of the presence of some strong hydrogen. But the main reason, we have exactly the same thing with infrared spectroscopy. The influence of the vibration, the influence of hydrogen bond is much more important than the ionic character itself. But the main reason, in our opinion, is that the acidity strength of a solid, or the acidity strength of any other material, depends not only on the ionic character of the bond, but depends also on the polarizability of the bond in the presence of the pairs. And so, in our opinion, it's absolutely necessary to define the acidity strength of a solid in the presence of an adsorbed phase. And so, we have chosen water. Why water? For three reasons. The first, as we will see later, we will have to do the simulation of dichron interactions. And it is, of course, easier to do it when we have a low concentration of proton. And in addition, we have only two similar protons. The second thing is that from the Pearson theory, water has an average, a good value of the hardness and softness. And also we had the old dream to try to find a relationship between the acidity of solid and the acidity in solutions. And so we have to study such a reaction that means OH group at the solid surface plus water. So either OH group are non-acidic at all, and so you must detect the OH group and water molecule without any interaction, or you have a low acidity and you may have such hydrogen bond, more or less important, or the solid is really very acidic and you must form more or less a large concentration of hydroxyl ion. And so it's necessary to find a spectroscopy able to detect these different interactions, no interaction at all, or formation of hydroxonium ion, more or less in strong interaction with surface, and here, low hydrogen bond or strong hydrogen. And as you know, high resolution NMR is a very good quantitative technique. If you don't torture too much the spin, using some special sequences and so on, you have really a quantitative relationship between the intensity of the line and the concentration of the proton. And so the question is now, is it possible to use high resolution NMR for determining the concentration of the different species we have just seen previously? And unfortunately, the answer is no. The answer is no, because at room temperature, when you absorb water or you absorb any other base, you have a very fast cyclic change of proton between the different species. And so instead of detecting many lines corresponding to the different species, you detect only one due to the coalescence of the previous signal. And of course, it's impossible from only one signal to determine not only the nature of the different species, but also the concentration. Of course, you can decrease the temperature. If you decrease the temperature at very low temperature, you will prevent such a fast change. But in that case, you have so large volume that even with a new sophisticated NMR technique, you are not able to average to zero, and so we decided, instead of trying to average to zero the dipole interaction, we decided to use this dipole interaction for the characterization of the equilibrium. But of course, we must know, if we want to dose the acidic center, we must know exactly the concentration of the acidic site. Because very often, at the solid surface, you have very acidic site, non-acidic site. You have different types of acidic species. And so in that case, you must use the high-resolution NMR. As example, this is the illuminated zeolite, and we see that you have 1, 2, 3, and maybe a fourth peak here corresponding. These are the acidic group. This is the silanol group. And after decomposition, we see that we have a small peak here corresponding to the aluminum OH concentration. And we must know absolutely the concentration of the acidic OH. So we must use the high resolution NMR. But you see that when you absorb water, you have only one line here. This one corresponds to the silanol group, proving that these silanols do not interact with water. But you have only one line here corresponding to the coalescence of the signal from acidic OH group absorbed water. And so it's impossible to use this technique for determining, for studying the previous reaction. And so we decided to use dipole interaction. I remind you that when you have, but in that case, if you want to use dipole interaction, you must be sure that you have really rigid lattice. So you must work at very low temperature, the base being, of course, 4 Kelvin. And so we absorb water at room temperature. We use high resolution NMR for determining the concentration of the different OH group. And after we quench the sample in liquid helium, and we have verified that we keep exactly the same equilibrium. And we study now the dipole interaction. I remind you that dipole interactions are very sensitive to the distance between two protons, since when you have such interaction between two spins, I and G, it has been shown that the dipole interaction is given by this value here. R is the distance between the two adjacent I and G spins, and you see that it is proportional to the reciprocal cubic value of the distance. That means if you change a little bit the distance between the two protons, you change very much the dipole interaction. And of course, it depends also on the orientation, but as we have a powder, we have, of course, all the orientation of these different liquids. And so, for studying such reaction, we must be able to do the simulation of the distribution of OH, the distribution of pair of protons. That means two protons in strong interaction. We will generally call X spin magnetic configuration, a configuration where we have X spin in a very strong interaction as compared to the interaction between adjacent magnetic configuration. And so we see that we have a two-spin magnetic configuration. We have a three-spin equilateral triangle and an isosceles triangle corresponding to the hydrogen bond. That means very often, if we have 1, 2, 3, 4 species, and of course, we have to define the distance between these two protons, between these three here. We generally have about 9, 10 parameters to be defined in order to have a good simulation of the spectrum. But as we will see, simulation is rather easy because the position, when we have such magnetic configuration, we have some resolved spectrum. That means the position of the maxima and minima strongly depends on the nature of the magnetic configuration. For example, this is a very well known, has been done in 1950 by Peck. This is a very well known doublet, that means two-spin magnetic configuration. Generally, when we use such a technique, we use a derivative of the absorption signal because we have much more details. And you see that it is symmetrical with respect to the center. That means I will show you only half part of the signal. And you see that when you increase the distance between two protons, you change really very much the shape of the signal. And if you are able to simulate such spectrum, you have immediately the distance between the two protons and the average distance between two adjacent magnetic configurations. This is another type of simulation which concerns triangle. We have an isosceles triangle. We keep R constant, the base, the smallest side, and we look at the variation of the signal, half part of the signal, the other part is here, when we change the ratio long side over the small one. And so you see the green corresponds approximately to the equilateral triangle, and here the ratio is about 1.6, the blue line, and you see that really the spectrum is very sensitive to the variation of the distance inside the triangle. We assume here that the interaction between two magnetic configurations was only 10% of the internal magnetic configuration. But now if you increase, here we have exactly the same variation, but we have increased the interaction between two magnetic configurations. And you see that first you have again, against the variation of the side, we have a large variation of the signal, but also you see if you compare the signal with the same color, the two green or the two red or the two blue, we have only changed the interaction between two magnetic configurations. You see that also in that case really the interactions are very sensitive. And so it's possible using this technique to determine exactly the concentration of the different species you have in the sample. As example, I give you the variation of the signal concerning a very good zeolite, which is rather rare. That means non-deilluminated, without any defect, and so on. And in that case, we have in such a solid, we have 48 acidic OH group. And when we absorb only exactly the same number of water molecules, 48 molecules, we see that we have in dotted line the experimental spectrum, in a full line, black line, we have the simulation, and to get such simulation, we need two lines, the red one corresponding to the hydroxonium ion, and the blue line corresponding to the hydrogen bond between water molecule and OH group. That means that if now you absorb either less water molecules or more water molecules that you have acidic OH group, you will need, of course, for the simulation, an additional signal corresponding to the residue of the OH group, if the number is lower than the number of acidic OH group. And of course, the signal corresponding to water, if the adsorbed water is stronger than the concentration of the acidic OH group. And if you look at the shape of the signal, you see that they are really very different, and especially the position of maxima and minima are very different, which proves that it is rather easy to do the simulation of the spectrum. So now a few words about the superacidic solid. First, the Nafion, as Georges Rollin said a few minutes ago. This is a chemical shift of the pure Nafion. We absorb water, a small amount of water. I always give the concentration of water with respect to the number of acidic OH. So here we have absorbed 50% of water with respect to the number of acidic OH group. You see that we detect only one line. And we have exactly one water molecule per acidic OH group. We have a narrow signal. We have only one line, and we will see later that we have only hydroxonium ion. That means that at room temperature, when you absorb one water molecule per acidic OH group of Nafion, you form immediately hydroxonium ion. And this is a chemical shift of hydroxonium ion formed with Nafion. Of course, the value of the chemical shift will depend on the interaction between hydroxonium ion and the solid surface. And after you see that you decrease the chemical shift when you increase water concentration, because of course the average chemical shift will decrease since the position of water should be about 450 ppm. The spectra are not very, very good because, as you understand, the concentration of proton in Nafion is not very high, and we have studied for such study, for such study, the spectrometer I got when I finished my PhD. Why you smile? This proves that you don't really need a very high sophisticated spectrometer for studying such a solid. It is a old 60 megahertz from barrier. Of course, it's a big improvement. And this is why you see that the experimental signal is noisy, but the red is simulation. And we see that we absorb one water molecule per 2 acidic OH group, and we see that we form in dark blue the hydroxonium ion, and we need 2 lines for the simulation of the OH group. We need 2 lines because, as it has been said, you have many OH groups in strong interaction because you have clusters. But you have also some isolated OH group. And of course, in that case, you have a Gaussian distribution. In the other case, you have a Lorentzian distribution. And so we need the light blue and the rose line for simulating the OH. Now if you have exactly one molecule per acidic OH group, you need only one signal corresponding to the signal of hydroxyl. Simulation is not very, very good because the signal itself is not good, but no problem at all. When you have one water molecule adsorbed per acidic OH group, you form exactly one hydroxyl. Of course, if you increase the water concentration, you see that you change very much the shape of the signal, and in that case, you have in dark blue hydroxonium ion, and in light blue the residual concentration of free water, and you see that we don't have anymore the signal of the OH group. That's normal because you have formed. All are engaged in the formation of hydroxonium. This is the abstract. Lower concentration of water, exactly the same concentration of water as you have OH group, and this is the second line corresponding to the residual concentration. And I don't have enough time to talk about it, but for each case it's possible to give not only the concentration of the different species, but also the distance inside each group, and the average distance between the different magnetic configurations. The problem with sulfated zirconia is a little bit different, because I don't know why, but this solid is a little bit hydrophobic. You can leave the sulfated zirconia in the atmosphere, and it doesn't absorb water for a long time. After 2 or 3 days, it doesn't change at all. So when you absorb water, at the beginning you don't have an interaction between the acidic OH group and water molecule. It is only when you absorb about half molecule per acidic OH group that you start to have formation of hydroxonium ion. This is, for example, 1.5 water molecule per acidic OH group, and you see that you have again the hydroxonium ion, residual water concentration, and the line corresponding to the residual acidic OH. That means that you need about 2 water molecules per acidic OH group to engage 1 acidic OH group in the formation of hydroxonium. That means you find exactly the same result we will have in a few minutes. That means you have a very strong acidic group, but the second one is like the sulfuric acid. You don't have any interaction between adsorbed molecule and the second OH group of the sulfur. If you increase the water concentration, you don't change at all the concentration of the hydroxonium ion. That means the second acidity is very, very low. Of course, I told you that the old dream was to try to have a parallel between the solution and the solid. And as it has been said that the definition of superacidic material is a material which has an acidity stronger than the sulfuric acid. We did exactly the same experiment with the sulfuric acid. We started with pure sulfuric acid and we add little by little water. As we have seen previously, we have only one signal, and the position of the signal, the chemical shift decreases, of course, with the concentration of water, because the average chemical shift decreases. But in that case, of course, we don't have any problem with detection. So you see that we have in green the experimental signal, in red the simulation, perfect simulation, and you see that you form hydroxonium ion. We have absorbed 25% of water with respect to the acidic OH group. And the residual concentration concerns, of course, the residual acidic OH. And when you have exactly one water molecule adsorbed per sulfate group, you see that you have hydroxonium ion, residual OH group concentration for such a perfect simulation. And now if you adsorb more and more water, you don't change the spectrum, except that you add more and more the compounds corresponding to the free water. That means, of course, we have found exactly what you know, that is that you have a very strong acidity for the first OH group and a very low one for the second. So we can define an acidity scale. Of course, for defining an acidity scale, as it is the case in liquid solution, you must fix the concentration of water. And so we have fixed the concentration one water molecule per acidic OH. And in that case, you see that we have here sulfuric acid, we have the nathium. That means that you have total formation of hydroxonium ion, alpha being the coefficient of dissociation of the OH group when we adsorb water molecule. Sulfated zirconia, 0.5, but in my opinion it should be a little bit greater because I told you the first molecule cannot be adsorbed, I don't know what the reason. Antimonic acid, and the interest when we have some zeolite solid is that we can, the technique is really very sensitive because you see it's possible to determine the coefficient of dissociation with respect to the silicon over aluminum ratio. And we see, for example, that the most important thing with zeolite is not the structure itself from the acidity point of view, of course, not about the free space. You see that the most important thing is the silicon over aluminum ratio, much more than the structure itself. And when we have really low acidity, it's possible to use the strength of the hydrogen bond because I told you that it's possible not only to define the concentration of the different species, but also the distances inside each magnetic configuration. And so when you have an isosceles triangle, because you have an hydrogen bond between water and hydroxide group, you are able to determine the distance inside such isosceles triangle. That means the distance between the two oxygen atoms, and so the strength of the hydrogen bond. And when you have a very low acidity, you can use this hydrogen bond strength for determining the acidity of the solid. And so we have now an acidity scale that we can use from non-acidic solid at all till superacidic. And thank you very much for your attention.
Thank you, Jacques. In view of the time, I think we will take one question only. There is one.
Jacques, I'm interested in what you've learned with the NMR for the Nafion and how well it seems to correspond with what people like Sundal were learning 30 years ago from infrared spectroscopy for cross-linked polystyrene sulfonic acid. And I think that maybe if you go back and look at that and then use this to cross-link polystyrene sulfonic acid, you get a very precise effect of the fluoro groups in the Nafion and the effect of the acidity. Please comment about that.
No, the only one, yes, I agree with you, but the only one problem is that they use infrared.
Yeah.
Yes, and the infrared is not a quantitative technique. That's the main problem.
Right. But it gets structural information.
Yes.
It seems to agree well with
Yes.
yours.
Thank you very much again, Jacques, for an interesting talk.